This lesson is on function operations and composition of functions. This is section 1.6 from your book. So similar to how we can multiply, divide, subtract, or add numbers to functions, we can also multiply, divide, subtract, or add functions to other functions. So we know that we could take some function and add 5 to it, or we could take some function and divide it by 2. So in that same respect, we can also take one function and multiply it by another function and use that as our operation. So something to remember from algebra before we go on is the distributive property. The distributive property says that A times some quantity B plus C is equal to A times B plus A times C. So that works very similar to the way that we will be looking at these functions and what they are equivalent to. So let's start. The first one is the sum. So our sum means that we have some function f plus some function g evaluated at x. This is equal to the function f evaluated at x plus the function g evaluated at x. So we have f plus g of x, and we end up with f of x plus g of x. The next one is the difference. This works very similar to the sum. We have f minus g evaluated at x, and we end up with f evaluated at x minus g evaluated at x. So f minus g of x is equal to f of x minus g of x. The next one is the product. And the last one is the quotient. So product is multiplication, quotient is division. So we can write these over here if you guys forget. So sum is addition, difference is subtraction, product is multiplication, and quotient is division. These terms over here are the ones that you need to know: sum, difference, product, quotient. So the product just works the same as addition and subtraction. We have some f multiplied by some function g evaluated at x. We end up with f of x times g of x. And the quotient is the last one, where we have some function f divided by g evaluated at x. And we end up with f of x divided by g of x. The only thing that's really important to remember about quotient is that obviously we have this g of x in the denominator now, and we know that our denominator cannot equal 0, or we're going to end up with an undefined function. So this f of x over g of x only works where the g of x does not equal 0. So you might have some x's in your domain that don't hold for this new function. So in addition to combining functions by addition, subtraction, division, or multiplication, functions can also be combined by composition. Oops, let's go back to black. So let's look at this example. We have h of x is equal to x minus 3, that quantity squared. So we know that that looks very similar to two other functions that we know. X minus 3 is a linear function, and x squared, or some variable squared, is a quadratic function. So we could write this as h of x equals x minus 3 squared, as the combination combines some g of x, which we're going to call x minus 3, that's everything inside of this square, and then also it combines f of x equals x squared. So if you were to treat everything inside this parentheses just as an x, you're sort of evaluating f of x squared at g of x. So again, this is called composition. And we write this as, it looks like fog. It's f with a little hole or a little dot, combined with, or composed with, g evaluated at x is equal to f of g of x. So we have f brackets g parentheses x close parentheses close brackets. So we're evaluating this function f at the function g of x. What does that look like? Let's do a couple examples really quick. So f of x equals x squared. If we were to evaluate that at x equals 2, we would write that f of x equals x squared at f of 2. And we can just, instead of this x, let's write parentheses. We know that's the place where we're going to fill in the variable. So we have some variable squared, and the variable that we have is 2. So another one that we can do is f of x equals x squared at f of a. So again, we have some variable squared. We're starting with our f of x. Start with f of x. And we are evaluating that at f of a. So we're going to have the quantity a squared. The last one we can look at, which is this composition, is evaluate f of x equals x squared at f of g of x, given that g of x is equal to x minus 3. So again, we have f, we write f, which is just parentheses squared, and instead of putting a 2 or an a in here this time, we're going to put an x minus 3, because we are evaluating it at g of x. Let's do another example. So find f of g and the domain of f of g. So we're given f is equal to 1 over x plus 1, and g is equal to x squared plus 9. So again, we write 1 over, and instead of that x, let's make sure we're just writing these parentheses, plus 1. The function we're evaluating it at is x squared plus 9, so we'll fill that in where we had our variable before, and we can actually simplify this. We have x squared plus 9 plus 1 is equal to 1 over x squared plus 10. That denominator, is that ever going to equal 0? It's important to check. But for any value, I mean, this is an x squared. Those can always be only positive, and then on top of that, we are adding 10. But if you wanted to check, you'd say x squared equals 0. X squared plus 10 is equal to 0. Subtract that 10 from both sides. You get x squared is equal to negative 10. Take the square root of both sides. This is going to produce some I. We have a negative under our radical. So we know we're okay. We know we're fine. That's not going to happen. So let me not erase the answer. 1 over x squared plus 10 would be your answer. And it would work for all real numbers. That would be your domain. The next one we can do is find f of g and the domain of f of g. So in this one, our f is equal to 1 over x plus 3, and our g is equal to 2 over x. So again, we write 1 over, we're evaluating f at g. So we're going to start by writing our f value. We're writing whatever is outside of here. If we have f of g of x, you want to start by writing your outermost function. So we have 1 over parentheses, because that's our variable, plus 3, and we're evaluating that at g of x, which is 2 over x. So we end up with 1 over 2 over x plus 3. So we have a fraction in our denominator. If you're not sure how to deal with that, all you do is multiply by what's in your denominator, and you can get rid of it. You need to multiply everywhere, though. Obviously, in order for this equation to stay equal, we can only multiply by things like 1, or divide by things like 1, or add 0. So in this situation, we're going to say 1 over 2 over x plus 3 times x over x. We're pulling that x out of that denominator in our denominator. And then we'll have to distribute that x to each of the terms. We end up with x over 2x over x plus 3x. This x cancels out from the 2x over x, and you end up with x over 2 plus 3x. Is there any point in this where we could have a 0? Sure, 2 plus 3x might equal 0 at some point, so let's find out where. So 2 plus 3x equals 0. Subtract 2, we have 3x is equal to negative 2 divided by 3. Divided by 3, we have some x is equal to negative 2/3. So for x equals negative 2/3, you can't do this. So our domain, where we're wondering where our domain is, it is going to be all real numbers except for x cannot equal negative 2/3. If we plugged in negative 2/3 into that equation, we would get an undefined function.